Welcome back, everyone, to part 3 of lecture 3 of MAE 170. So this is going to be the last part of this lecture, and we're going to talk about block diagrams. So block diagrams are very convenient, a very convenient way of representing control systems. And we've already seen them, but in this part of the lecture, what I want you to be able to do eventually is to simplify the block diagrams in order to find transfer functions. So let's take a look here at this closed loop system. So we have the most general way of representing the closed loop system, giving an input. So this will feed the sum injunction with the plus, and then going to the right, we're going to find the controller, whose transfer function is GC of S. Then we have the actuator, whose transfer function is G of A, or GA of S, I should say. And then finally, the process G of S. As I said, sometimes, or most of the times, the actuator doesn't have really a block on its own, but it's just together with the process in order to form the plant. In this traditional form of representing the closed loop systems, the upper branch, that is GC, GA, and G in series, is also known as L of S, or loop transfer function. I'm going to see that later on, but just for you to know. And then we have the sensor that measures the actual output, whose transfer function is named conventionally H of S. And the sensed actual output is fed back and compared to the input. And so we're going to have a minus. When you have some injunctions without a sign, it is, so if the sign is omitted, it is intended that it's a plus. And finally, we have the output, the actual output Y of S. So the objective that we have is to simplify this block diagram in order to find the overall transfer function. I'm going to call it T of S, that will take us from the input to the output. In other words, what we're going to do, we're going to substitute the whole system, which is one block, whose transfer function is T of S. Why am I talking about transfer functions of the controller, the actuator, and the process? Because if you just take a look at, for instance, the controller, and so if we cut this part of the block diagram, well, the controller will have its own input, and it will have the output. So G of C is still the ratio between the output and the input for the controller. And you can repeat the same reasoning for the actuator and the process and the sensor. So normally we will use T of S to represent the closed loop transfer function. Unless specified otherwise, T of S usually represents the closed loop transfer function, whereas L of S represents just the loop transfer function. So it's GC, GA, and G. Okay, so now we want to find an expression for T of S. How do we do that? Well, here I'm just rewriting the simplified system. So if we had just an input and an output, and we wanted to simplify the whole closed loop control system in one block, that block would be represented by a transfer function T of S. In order to do that, we need to know just a couple of rules for block algebra. So how to deal with blocks. You can find in the textbook and elsewhere many rules, and sometimes they can get a little bit confusing. So I'm going for a more straightforward approach for the block diagram reduction here. So the only two rules that you need to know are very, very easy. When you have blocks in series, such as in the upper branch of the block diagram, for instance, we have GC of S, GA of S, and G. So if you have like a train of block diagrams, you can substitute this train with just one block whose transfer function is the product of the single transfer functions. And for this case, we have that this product is indeed L of S. So very easy first rule. If you have blocks in series, you can multiply their transfer function and find a equivalent transfer function, which is the product of the singles. The second rule is just that if you have a signal and you have the signal splits, well, it maintains, the signal remains the same in the two branches. So after the split point, you have X of S going straight and going downwards. That's very easy. In other words, you don't have that part of X of S, just, I don't know, half of it goes one way and half of it goes the other way. In order to get that, you would need a sum injunction. So if you don't have a sum injunction, whatever splits just remains the same. And in fact, the sum injunction, well, this could technically be categorized as a third rule, but it's very, very easy. You just have an algebraic sum of the signals going in. So you see that the signals are also characterized by functions in the S domain. So for instance, A of S that is fed into this, the sum injunction has a plus, and then we have B of S with a minus. This is just arbitrary. And the result is the signal C of S. So C of S is A minus B. So you see here that, as I was saying, signals and transfer functions, they're all depicted with, capital letter function of S. In fact, if you didn't know, mathematically speaking, they are equivalent. A transfer function, so something that describes what's inside a box, or the signal that travels between boxes, mathematically is the same object. They are both functions of S. All right, so now let's get to the actual solution or simplification or reduction of the block diagram itself. So what you need to do in order to simplify the diagram, well, we'll need to come up with n+1 equation. So we'll have to solve n+1 equations. What is n? Where n is the number of sum injunctions. So if you had 3 sum injunctions, you would have to find 4 equations and solve these 4 equations, a system of 4 equations, as easy as that. All right, but we have n sum injunctions. Why do we need n+1? So how do you get the remaining equation? Well, that is given, or it is associated with the output y of s. And I'll tell you, I'll show you right away how to do things. So procedure, step number 1, very, very easy. Count the number of sum injunctions. And let's apply this to our example. Although it's very generic because it just depicts a common closed loop system, but we do have, we can apply that to find T of S. Okay, so how many sum injunctions do we have? We only have 1. So n is equal to 1. Step number 2, we need to name, so to give a name to every signal after every junction. So just give it a name. Here, in this case, for the closed loop system, in the traditional way, we have that the signal, that is this arrow here, coming out of the summing junction is the input minus the measured output times the sensor. So this is the error. So we'll just call it E of S, but you can call it with any name, of course, as long as you haven't used it to name the input, the output, or one of the blocks. So in this case, E of S. And now we're ready to find the equations. So how do you find the equations? So it's easier to do it than to describe it, but let me just try to describe it. So what I wrote here is using the rules above, so 1 through 3, blocks in series, splitting, and summing junctions, you have to write an expression for every signal found in step 2. So in this case, E of S, by going backwards until you hit another known signal, and then repeat for the output. So you do the same thing for the output. All right, let's see what it means practically speaking. So for our example, I forgot to fill in step number 2. Step number 2 is just the error because we had the summing junction with the input with a plus, and then whatever signal we have here, it doesn't really matter, but we want to name what comes out of it, and we named it E of S. All right, so now step number 3, we have to write these expressions. So starting from the first signal after the summing junction, that is E of S, we go backwards until we hit signals that we know. So what that means is that E of S now is equal to, since we have the summing junction, is equal to R of S, and this is a signal that we know, it's the input, minus, we travel backwards, H of S times, and we go backwards, and here you see the splitting, and we know that after the splitting, we have Y of S, but for property number 2, this is the same signal that goes also down. And so H of S times Y of S. It's easier to write it down. So step number 3, we have n+1 equations that we need to write, one for E of S and one for the output. So for E of S, we found that E of S is equal to R of S minus H times Y. And then let's do that for the output, because that's the only thing that we have left. So the output, starting from here and going backwards. So now we have the summing, or this summing junction. We have this splitting point. Do we go downwards or to the left? Well, if we went downwards, we would go with, we would go forward in the direction of the arrow, but we always want to go backwards. So we have to proceed to the left. So Y is equal to G times GA times GC times E. And we stop here because E is one of the known signals. So Y of S is equal to G times GA times GC times E. And as I said earlier, we can call all this block here just to simplify L of S. And you see here that you have 1 and 2 equations. Since n is equal to 1, well, we have n plus 1, which is 2 equations. All right, we're pretty much done. We're left with step number 4. We need to solve